In this model, our robot will move in a square instead of moving forward and back. All we need to do is change the state flow chart, and our Simulink diagram can stay mostly the same. After we have created our 4 states, we move our default transition, and then we are going to create a loop. I create the loop by bringing a transition back to an earlier state. Notice that when I have a second transition from the original state, the transition is labeled number 2. In our default transition, I will now define a variable called count, which is set to 0. The variable count is an internal variable that will be used as an index counter to keep track of how many times we have progressed through the loop. While we are in a state, each time we will now define 2 output variables. We use the command during : to define these variables while we are in the states. One output variable, speed L, is for our left motor, and the other output variable, speed R, is for our right motor. Every time we enter this state, the value of the variable count will be increased by 1. And this is denoted by the command entry : In the remaining states, we define the values of the output variables speed L and speed R and use after several seconds for our transitions, similar to the previous lesson. The amount of time that your robot spends in the turning state will of course depend on the design of your chassis and the size of the wheels. The second transition, which is labeled with a number 2, has a conditional statement which is identified by square brackets. Inside of this conditional statement is a test to see if we have completed 4 loops of the model. When the internal variable count has reached 4, we move to the final state where the motion of our robot will cease. When we update our Simulink diagram using the keystroke Control-D, the symbol wizard will open and we will see that we have 1 local variable called count and 2 output variables, speed L and speed R. As a final step, we need to draw signal lines from the 2 outputs of our state flow block to the motor blocks, which you can see in the Simulink diagram. If we run a simulation of our model using the field simulator, you can see our robot moving in a near-perfect square. The values in our model that work in the simulation may not work with the physical robot. This is because our simulation did not account for the actual design of our chassis. As we can see, the robot is not moving in a perfect square.